Okay, got the recording started, the slide up, so I think we're ready to go. Um, this chapter 7 on antennas is probably one of the most important ones to spend some time on and understand. Um, you look through the ham radio magazines, and there's all kinds of fancy equipment that does this and that, and fancy transceivers and noise eliminators and all this stuff. But what it boils down to is if you don't have a suitable antenna, none of that stuff's going to help you very much. So it's important to understand antennas, and not in great detail, but at least conceptually what's going on, so you can try to figure out what the best solution is. And I think one of the most important aspects of figuring out what kind of antenna you want is, before you start even looking at different types of antennas, is really define what you want to do with this antenna, because that's a good practice in anything that you're looking to design, and it's something that you're taught in engineering, that problem statement is the first step and could be the most important step. So think of it in terms of what you want the antenna system to be able to accomplish. And then not only that, but think about what you can give up that you don't need in this particular antenna system. Because the way Mother Nature works, in order for you to get something, she's going to take something from you. So you need to understand those trade-offs, and based on your problem statement, and then evaluating the trade-offs, you can work your way to a pretty good solution. So that's just kind of my opinion. You can take it for what it's worth. So we'll get into the meat of the stuff here. So in this chapter, we're going to touch on antenna basics. We'll take a look at dipoles and ground planes. Probably the earliest antennas you start to work with will be dipoles, and maybe verticals that use ground planes. We'll look at the effects of antenna height and polarization. There's a directional type of an antenna called a Yagi. You can see the picture on this page. The guy's holding those two antennas. Those are Yagi antennas, characteristically a long beam with elements perpendicular to the beam. You see these a lot on radio towers hams have, and that particular application that they're doing there is a satellite communication, where they sweep the sky with that antenna as the satellite passes, and do the communications. We'll touch on loop antennas. I've never had any experience with loop antennas, but we'll talk about them a little bit. Certain antennas with special characteristics. Feed line basics. The feed line is what goes from your transceiver to the antenna. So there's some things you need to be aware of there. And then we'll take a look at SWR and impedance matching. And SWR stands for standing wave ratio. And what that is, it's a measure of the energy transfer efficiency from the transceiver to the antenna. And we'll see what happens to the energy as it's being transmitted. Not all of it goes out the antenna. Some of it will come back to the transceiver, and that's what the SWR is used for, to help us understand that a little better. So I always like to get back to the basic science of things, and I think we may have touched on this in the technician course, but in order to, if you look at an antenna and you want to try to conceptualize the radiation pattern, I think it's handy to understand Ampere's right-hand rule. And that's a real simple rule that if you point your thumb in the direction that current's moving in a wire, parallel to that wire, then the magnetic field is going to be circular around that wire in that direction. So the magnetic field radiates from that wire in all directions, 360 degrees out. And when the current reverses like it does every cycle in an RF signal, then the magnetic field reverses, but it still goes out, but opposite polarity in the atmosphere. So if you, let's say you had an antenna that was straight up like that, and then let's say it bent at a right angle, and if you use Ampere's law, you can see as you orient it on this section of the antenna that's vertical, the magnetic field is going to radiate out from the wire. And then as it makes that bend, your thumb's going to go horizontal now, and then that radiation is going to still be coming out from that wire, but now it's horizontal, so that it'll be going out in those directions. So you can kind of visualize with this what a radiation pattern might be on a particular antenna you see, particularly some that may be a little unique or different than what you're accustomed to. So first thing we'll look at will be antenna elements. Now the elements are the part of the antenna that radiates the electromagnetic energy. And if we look at a dipole, this is a half-wave dipole, and it's called a half-wave dipole because the overall length is a half a wavelength. So that this was 40-meter dipole, this half-wave length would be 20 meters. And then a quarter wavelength for 40 meters would be 10 meters. So the actual antenna elements are 2 quarter-length wavelength wires. And so they'd be about 10 meters each. And then you have your feed cable. It could either be a coax or some type of ladder line, several different ways of doing that. But in this case, the antenna elements are the wires that are horizontal that carry the current, and it splits into the elements from the transceiver. Now this is a little more complicated, a little busier antenna, but this is a Yagi antenna, and this particular antenna has 2 bands that it's operating, has the capability to operate. There's a high frequency band and a low frequency band, and they're not being exact on what band it is. It's just showing that one band is higher frequency than the other. So if we go through and look at the low frequency elements, we'll find right here is the driven element for the low frequency. And the lower the frequency, the longer the wavelength, so it has a longer element than the high frequency driven element. So you get a nice long driven element here, and this is where the feed line connects to the antenna. And then these other elements, they're also conductive parts of the antenna. They're not connected to the power feed from the transceiver. They're in free space. And what they're doing is, if we look at this driven element here for the low frequency, there's another element back here called the director. Well, that's high frequency. Whoops. There's the reflector. There's a reflector for the low frequency, a driven element for the low frequency, and there should be another low frequency, but I don't see it. Okay, so this is a 2-element low frequency antenna. So we're driving this element here. And if remember Ampere's law, we put our right-hand thumb out, we can see that magnetic field is going to be radiating from that antenna because of the current flow in the antenna, and it's going to be radiating around this element, and it will intercept this antenna, this reflector. Now this isn't driven, but what happens when the electromagnetic field contacts this free space element, it'll induce a current in the element, just like a receiving antenna would. And because of that current, and the power level of the low frequency signal and the proximity being close to the driven element, it'll have enough current that it'll re-radiate that signal. So what you have coming out this way, this will have the magnetic wave propagating out from it. This one will also have a magnetic wave, just like this one, and that'll flow back this way, and they'll add, and that's how you get more power directed in one direction. And then you can have multiple directors and reflectors like they're showing on the high frequency antenna to get more gain. Now they talk about gain in an antenna, and it's important to understand the gain in an antenna isn't like the gain on an amplifier where you turn the knob up and you get more power out. With the antenna, the power is pretty much constant that you're pumping into the antenna. And what you change rather than the power level is the focus of the power. It's kind of like a reflector in a flashlight, where say if you have a parabolic reflector, it'll focus the beam. You still have the same amount of light coming out of the element of the light bulb, but you can, by adjusting that reflector, focus the energy into a smaller area, giving you a higher effective energy in that direction. So that's what gain is when they're talking about gain on an antenna. So both of these antennas would have more gain in one direction than a single element dipole. Now the cost, what you give up for that is you get more gain, say, going in this direction, but the gain perpendicular to that is much lower. So you're not getting as much power out the side of the antenna as you would with a single dipole, but you are concentrating the power coming out of the antenna into the direction you want it to go. And that's why a lot of yeah, go ahead.
Well, okay, so you have your driven element and that hits your reflector,
right?
And then the reflector basically literally reflects it back. What drives it one direction versus the other one?
Well, they're gonna go in all directions. But what you get,
but I mean, if it reflects it back to the driven element, I would think there'd be more power to driven element, so you'd want to go through the reflector.
Well,
as opposed to
think about
coming back to the left.
Let's sit on this electromagnetic wave on the driven element, and as the current's flowing, that wave's moving towards the reflector, and as it cuts through the reflector, the changing magnetic field induces a current in the reflector. Now, anytime you have a current flowing, you get a magnetic field. So you're going to generate another magnetic field going to the right, top right, and then also back to the left. And what that'll do is it will add with the magnetic field that's already heading out from the driven element. So it's like, depending on, let's say you get 25% the power re-radiated off of this reflector that you had in the driven element. So then you have 12.5% going one direction, 12.5% the other.
Right.
So that 12.5% adds with the driven element as it goes out into the atmosphere. And then there's a director,
which basically you're saying it's going to go to the left in this particular picture.
Right. And there's two types of elements on the Yagi, well, three, the driven, then there's a reflector, and then there's a director. And I forget which is which. I think the reflector's a little longer than the driven element, and then the director's a little shorter. And that gives you the directionality of the concentrating the electromagnetic wave.
Okay, because that's what I was wondering. I mean, if your driven element in the middle there is going to the right and it's setting up a current in your reflector, why would it not just keep going and add to the signal coming out of the reflector on the right as opposed to reflecting back? What prevents that?
Well,
I mean, I realize it is, but there's more direction going left.
And then you have a similar action on the director. So
Got it. Okay.
now, if you look at some of the Yagis, they may have 6, 8, 10 elements, and that's where you're only driving one of them, and you have a bunch of reflectors and then one director on the backside, I think it is, and that focuses more and more energy into the direction you want to go. So what
Got
they
it.
do is they'll put that type of an antenna on top of a tower with a rotator, so you can spin 360 degrees and point to whatever compass setting you want to focus your signal. So if you're trying to get, say, Northern Europe, you can focus most of your energy from your antenna to that in that direction.
Right. Right. Okay.
So that's what a lot of these guys with these big towers have. They have multiple element Yagis on all these bands and 1500 watt amplifiers, and they can go all over the world with those things. Of course, they aren't cheap. So that's kind of the one of the most basic, and there are a lot of different directional antennas, but this is one of the basic designs, the Yagi for directional antennas. Now, the next thing we look at in order to understand antennas and try to draw visually what's going on is the idea of a radiation pattern. And what that does is it refers to the power, directional power that's given off by a certain type of antenna. Now, there'll be questions about this on the test. And the one antenna that's a reference antenna is referred to as an isotropic antenna. And it's a fake antenna because you really can't build one, because all it is a single point in space that if you could radiate from a single point in space, which you can't because you need current flow, you just can't have contained charge to generate an electromagnetic field. You can have an electric field that way, but you can't get the electromagnetic field with a single point. And theoretically, the radiation pattern from a single point would be a sphere. As you go out, the signal gets weaker and weaker and weaker, but it's uniform in all 360 degrees, like the sphere. And when they refer to gain, because the gain that you are measuring or referencing for a particular antenna is gain reference to a standard. And like this is a standard reference antenna. And if you see the units on an antenna gain figure is dBi, that means it's decibels reference to an isotropic antenna. So if it has a gain of 3 dB, 3 dBi, that particular antenna has 3 times the gain of an isotropic antenna. Well, actually twice the gain, twice the power, but it would be 3 dB because 3 dB is a double from the reference. So it's just a point of reference. And when you do start looking at antennas, if you haven't already looked at VHF and UHF, you may see them in the catalogs and on the websites talking about their gain. And it'll either be dBi for reference to this isotropic, or dB, forget what it is, but it's reference to a dipole, so it must be dBd. So you have to compare, when you make a comparison between antennas, make sure that they're using the same reference. And if they aren't, if one's dBi and one's dBm, then there's an addition or subtraction you make to get them on the same field. So that's the isotropic or fake antenna. And then the other reference antenna is a dipole that we looked at earlier. So that'll be dBd. Okay, now if we take a look at the radiation pattern of a dipole antenna, And this is physically what we have. We have a feed line, and the one side, the center of the coax goes to one element, and then the coax shield goes to the other element. And then we have some sort of insulator here that will interface between the wire and the rope, and then this rope goes to whatever supporting structure you may have, be an antenna mast, a tree, just whatever you have up there. And that way you have a fixed wire length in free space. Now, when you power that dipole with an RF signal, the radiation pattern is going to look like this donut, where the elements are running north and south here, for example, in this direction. So your radiation is going to be around the elements and going out in all directions, up and down to the ground and out across the surface of the earth. If you take a slice through this donut and look at the cross section, this is what your propagation would look like with the wire going into the page. Now, in practice, you don't, this is a null because it's a point where you don't have very much gain. You have very little, if any, signal going out in that direction. So if this antenna was pointed north and south based on this theoretical radiation diagram, you wouldn't expect to be able, say, from where we're at now, to hit Florida and get signals down there or receive signals based on this theoretical radiation pattern. But in actuality, in a real dipole, it's a fairly similar shape here, but it doesn't go to zero. It just kind of flattens out here, so you do get propagation off the ends of the dipole. So you can work on a north and south oriented dipole. You can still work folks down in Florida, Cuba, down into South America. It's just that the gain will be a little lower here. You won't have as strong of reception or transmission, but you can still operate off of it. So when you look at, particularly, there's a lot of modeling software that you can model antennas and see the so-called propagation pattern. But the thing to keep in mind is that's theoretical, and it may not actually look like that. There'll probably be some slight modification when it gets in the real world. And the easiest one to see is this dipole, where it's actually more omnidirectional than having these nulls here on the wire plane. So that's kind of what the radiation pattern looks like. Now, when if you recall from the technician class, we talked about bounce off of the ionosphere. And this is where the part of the signal that goes up to the ionosphere propagates through the atmosphere. And you can get pretty good distances that way. Then the lower this web is, or this part of the lobe is to the ground, the more ground wave you have. And for DX and things that are pretty far away, like to have a low ground wave or takeoff angle. So it just depends on what you want to do, what kind of antenna you want to use, because of the propagation pattern would be one consideration in your decision process.
Now, in that case, back up one.
Yeah.
In this case, if you took this antenna and turned it like 45 degrees,
Yep.
wouldn't that, so then you would have your propagation head out at 150 with a higher gain, correct? Wouldn't that be a better way to go further, bouncing it off
what
the
you run
ionosphere?
into, and we'll get to it in a couple of slides, is how the antenna responds with the ground and the height
Okay.
it is above ground. But yeah,
Got it.
generally,
All right.
if you were up in free space like that and rotated it, yeah, you're right, that propagation would go up at a 45-degree angle So you'd have your main lobe going up that way.
Okay. So in theory, great. In actuality, not so much. Okay.
Right. Yep. Now this is a radiation pattern from the Yagi antenna, the directional antenna, where you have your driven dipole here, and then the directors, and these are just static elements. And because of the number of elements, directors going this way, most of your propagated energy is in this direction, and that's what this lobe is showing. So you can see you still get some signal out the back because you can't get it all going forward. And the more elements you have, the tighter angle this is. If you had more elements on this antenna, you could concentrate the power in even a narrower angle, so you get more power going out, which should get you farther distance. But there again, it's a trade-off. You need more elements to get a higher gain and tighter propagation lobe. So you could see easily as if this was where the antenna was mounted here on the, say on a tower with a rotator, you could easily swing this lobe around in any direction to get what you want to see or contact. So this is the main lobe on a directional antenna, and you will get a back lobe as well. And the more elements, the less the back lobe, because you get more redirection of the energy to the forward lobe. So there again, it's another trade-off. You can receive and transmit off the back end. Say if you're pointed towards Northern Europe, this would probably be up at say 45 degrees. Well, you'll still have lobe transmitting and receiving off the back end, say down into Texas and Arizona. It just won't be as strong as what you're sending and receiving on this main lobe. So that's how a directional radiation pattern looks. And then, so that was, we looked at the dipole, we looked at the Yagi, which is a directional antenna. Now this is a quarter wavelength vertical antenna. And a vertical antenna is nothing more than a dipole rotated 90 degrees and half of the dipole's missing. You just put the actual wire up, whether it's a post or however you're doing the main element. And then in order to have the balance to accept the energy from the negative part of the cycle, you need to give it what's called, referred to as an electrical image. So it appears to be the other half of the antenna, the other half of the dipole, but it isn't really. It's just a capacitance that can absorb and store that energy on the negative part of the cycle or half the cycle, and then return it back to the system. So there's several different ways. You can do a conductive ground plane, and electrically this looks like the half of the dipole antenna is not there. You can have radials, which are multiple wires of different lengths going out from that feed point on the other side of the coax cable coming in. And so this is the driven element. Then you can have the radials. And then there's, I forget what, I'm drawing a blank. Counterpoise. You can use a counterpoise, which is just a long length of wire that's running along the ground that isn't radiating or isn't adding to the radiation of the antenna, but it does provide the second half of the antenna for it to balance the current flows. So when you're looking at an antenna, vertical antenna, just think of it as half of a dipole. And when you think about the propagation, if you use Ampere's right-hand rule, point your thumb up, the magnetic waves are going to radiate unidirectionally from that antenna. The same thing. The wire doesn't know if it's horizontal or vertical. So if it's vertical, it's just going to radiate the magnetic field omnidirectionally with the antenna in the center. Now, if you've got a mobile VHF, UHF radio in your car and you're using a mag mount, what you're doing there effectively is using the roof of the car as a ground plane. So if this was a UHF, VHF antenna into the mag mount, the roof of the car provides this ground plane effect through the mag mount, through capacitive coupling through the mag mount. That's why you could also use, if you're in the house, you could use a filing cabinet or refrigerator or stove or anything like that as a ground plane for your VHF and UHF type antennas. Okay, and then this is looking at the radiation pattern of that vertical antenna. Again, it looks like there's a major null in the center, but since it's a real world antenna, there will still be some propagation up in this part going up here. Now this particular antenna, let's see what they're talking about. Here's the feed point where your coax comes in, 50 ohm coax. And then these are the radials that go out into the ground or on the ground. Usually looking at 10 to 20, anywhere from 5 to 10 meters in length. Have to have some sort of a support system, some guy wires. The radiator wire, they're using 18 gauge, and it's 33 feet long. And then 12 meter or 40 feet spider beam fiberglass spider pole. So this is one configuration for a 40 meter vertical. This is about 40 feet high, which is close to, let's see, 40 feet, that'd be 10 meters. I'm not sure that adds up. Oh well. So that's typically a schematic of what you might see in a vertical antenna using the radials. And then these are cross sections of this 3D radiation pattern, to where you can see this is from the top down. This bottom plot's from the top down, as if you're looking from the sky down to there's the tip of the antenna, and it's going to be uniform in all directions. And then if you cut a slice through it, you're going to see radiation lobes like this as they propagate from the antenna. So the propagation pattern is a little different with the vertical because of the 90-degree switch from the horizontal dipole. Then there's another type of directional antenna. It's called a log periodic antenna. And what it does is, you can see these elements aren't equally spaced, but it's designed so that there's some multiple logarithm for the different bands that gives them the spacing for the elements. And the advantage of this antenna is that it has a very wide bandwidth of frequencies that it can operate on. See these sometimes in TV antennas, but in the old days with the towers. But it gives you wide band performance, so you could operate this antenna on any one of a number of bands without having to change antennas. But the one downside is it has fairly omnidirectional radiation pattern, so you really can't focus it. You would think, looking at this pattern here, you could put directionality onto the signal like you do with a Yagi, but it didn't work out that way. I forget what the frequency range is on these. So it's a wider bandwidth, but not as directional as a Yagi. And they're usually pretty expensive. I've never really understood why they're that expensive, but I haven't dug into the design, how they build them yet either. So that's, you may see those in the catalog, or may have a solution, problem where this would be a good solution for you. Okay. Now the loop antennas, like I said, I've never used one, and I don't have a real good feel for how they work. But I do know that the radiation pattern for the loop is dependent upon the wavelength or the fractional wavelength that you drive the antenna with. They're usually pretty low noise antennas, but maybe the book gave you, would be hard to give you more information than I just gave you, but they do have applications, generally lower power. They do better with higher noise environments. They're not as susceptible to noise as, say, the vertical or the horizontal dipole. So it would be a consideration, but the radiation patterns are quite different depending upon the fractional wavelength that is driving the antenna. This is, we're going to take a look at the effects of antenna height above the ground. See what happens if I click that. Oh, okay. What this is I went through an analysis on a 20-meter dipole on the height above the ground. So for 20 meters, one wavelength is 65.6 feet, or half wavelength is 32.8 feet. So started off with a program called ESNIC, which is one of the antenna modeling programs. And I modeled the 20-meter dipole at 10 feet above the ground and looked at the propagation pattern. And you can see, in this case, the antenna dipole will be running into perpendicular into the page there at the bottom of the axis right here. So the antenna is running in and out. And this is what you would see the radiated energy at 10 feet. Then if you raise the antenna to 20 feet, you can see you're getting more propagation to the sides in the direction you want it to go. So that's a little bit better radiation pattern than we had at 10 feet. And then you get up to 30 feet, which is almost half a wavelength. And then you see we start getting these lobes develop where we're getting most of the energy propagated out here at some desirable angle for good distance coverage. And then if we go to 40 feet, which is over half a wavelength, then we start getting some of the energy start going back up vertically, but we're getting flatter lobes, lower angle lobes, which is better for propagation. So this is a good direction to go if we're wanting distance propagation. And then you could actually get it up a little too high because if you think about it, you're sending a lot of energy vertically that's not doing you any good. But the advantage is that you're getting an even lower takeoff angle, which should get you more distance on your propagation. And then at 60 feet, you get pretty low angles of propagation with kind of a bizarre, you'll probably get propagation off the ionosphere here and here, but it's definitely changing the propagation pattern of the antenna just by changing the height of the antenna above the ground. And so if you look at this graph from the results, this is the height above ground. And what we're looking at is the max gain angle. And that would be the blue line. You can see that the higher we go, the lower the maximum gain angle is, which is the direction you want to go. Say if you're looking for dx, distance contacts and that kind of thing. And then the gain, the focusing of the energy, you can see here it's maximum at about 40 feet above the ground, but then as you continue to increase the height, you actually lose gain from the antenna. So this slide's kind of a summary of how the height changes your propagation pattern as you go from 10 feet to 60 feet. And regardless of the band the dipole's on, they would all tend to look, have the same general configuration, just be different frequencies. Does that make any sense?
Real quick question.
Sure.
So at 30 feet, we have kind of those little bubbles started.
Yeah.
And at 60 feet, there's similar things started there.
Right.
Is that due to harmonics?
I don't think so. I think it's more interaction with the ground effect, because the ground is a, hesitate to say a good conductor. It varies with the ground type, with the type of soil you have, but it will dissipate and reflect energy depending on the ground structure, what type of soil it is. Now, where you get into some issues, why these are just kind of general tendencies, I've got 3 horizontal dipoles up in my backyard. They're all, I don't know, I think the 80 meter starts off at about 75 feet above the ground. But my yard slopes down to the lake at a pretty steep angle of about 30 degrees. So the dipole's horizontal, but the ground's dropping away from it. So I don't have a clue as to what, how I would go about modeling it. I didn't want to spend the time to try to model it. But by looking at these, I can see that I would imagine what's happening. Let's say the part of the antenna that is up the top of the hill would have a propagation pattern like this half. And then as it starts moving, the antenna staying horizontal, but the hill's dropping off at an angle, I would tend to get to have more and more of these flatter lobes going out. So I think it's an asymmetric propagate. Well, I know it'd be asymmetric, but I think I get the good low lobes on the downside, the downhill direction. And it turns out, I don't know if I could prove it or not, but that's going towards Texas. And Texas is, in my log, the most common contact I have in my log. So
there you go.
that may be, that's kind of not really empirical evidence, but something suggests that that's what the propagation waveform may look like. So that's what you have to do, is if you kind of understand the basics, you can kind of walk your way through, well, what would this do? And, you know, so it looks to me like my propagation pattern will look like half of this on one end and then probably over here on the other end. So it'd be kind of an odd beast, I guess. But the real fact of the matter is how it performs. And I've been getting real good performance from them, so I must have lucked out there. Okay, so that was a little sidestep there. Okay, now we'll get into antenna gain. And you remember earlier I talked about the difference between the isotropic antenna gain and the dipole antenna gain as the references. The difference between them is 2.15 dB, decibels. So if you're seeing an antenna table in a catalog where one manufacturer is listed as dB or dBd based on a dipole, and the other guy's using the isotropic antenna, you have to adjust the gain on the dipole or the gain on the isotropic by this 2.15 dB, so you can make a comparison. So that's just something to be aware of. You just can't look at the numbers. Okay, this is right out of the book. Different types of antenna feed lines. The only feed lines that I've used so far have been coax, based on the antenna designs that I've used. But in addition to the coax, which is generally a center conductor with an insulator and a braided conductor on the outside of the insulator, and all covered up with an outer jacket. And there's just variations of that basic configuration. This one here, for example, has 2 layers of the shield. Not sure what you'd be doing with that, but it sure wouldn't be cheap. You'd really have to make sure you needed that before you'd want to use it. Then there are other types of conductors where it's 2 parallel wires separated by an insulator. This is a 300 ohm twin lead. And this was used a lot in the old days when we had outside antennas for televisions. In fact, I remember when I was a kid, my dad hooked up some of this 300 ohm twin lead, split it, and made a dipole out of it so we could receive the antenna radio, TV signals better. Then there's also 75 ohm twin lead, which has to do with the impedance of your wanting to match the impedance of your transceiver in the antenna. There's the 450 ohm window line, where it's the same thing, parallel wires with an insulator between them, and this has little windows cut out of it. So each one has different uses, and as you get into selecting an antenna, then you start looking at the feed line. You need to do a little research on what the best type of feed line would be for that particular application. Now we're going to get into kind of a neat area, at least I think it's neat, on wave reflection and standing waves. Because what happens is that when you're transmitting an RF signal from your radio to the antenna through a feed line, the energy will go down the line, and if the impedance at the end, the antenna impedance, perfectly matches the transmitter's impedance and the feed line's impedance, and then the antenna, if they perfectly match, then all the energy will be radiated from the antenna. If they don't match, you're going to get a reflection. Let's say the feed line's 50 ohms and for some reason the antenna is 60 ohms. There's going to be, because of that mismatch, some of that energy is going to be radiated, but the rest, the energy that isn't radiated because of the impedance mismatch, is reflected back to the transmitter. So that's where we're going to take a look. I'm going to start up this YouTube video, I hope. And see what this is. Okay. May have to go looking for it here a little bit. Well, I may just open it up directly. Okay, I'll go looking for it. Let's see, ham radio, chapter 7. Okay, here we go, ripple tank. Okay, let me pause it here if I can, kind of explain what we're doing. I don't know how this is transmitting for you. Okay, so I paused it. Actually, I restarted it. Well, the mouse is.
It looks all right so far.
Can you see the waves, the ripples moving?
Several still pictures, basically.
Oh, okay. I'll just attach these videos when I send you the slides. Maybe the recording will pick them up okay because it's not going out through the internet since I'm recording here locally. But what's happening, you're seeing the ripples on the water that's in the tank above. And as they ripple, they'll hit that block on the left-hand side, and some of the ripples will reflect back. Now, if you had a perfect impedance match between the water and that black block, there would be no reflection. So the more the mismatch is between the water in this case and that block, the more reflection you get back from it. And not only is this used in tuning antennas, but it's also used in stealth aircraft where they're trying to redirect or absorb the radiating energy from the radar, which is an electromagnetic wave, and keep it from reflecting back to the receiver. So I'll see if that shows up better in the recording.
I think it's slowly coming through, but yeah, it's not great.
Yeah, you're probably not seeing the reflection very well because it's fairly faint. But I'll take a look at the video that's recording and see what that's up to. And then the other one, actually, this is also a video off of YouTube, and I don't think it's going to show up very well. I'll send you the link to that, to this one as well. But what this is, it shows standing waves in a transmission line and the effect of resonance, where you start getting multiples of your resonant frequency on a standing waves in a transmission line. It was a pretty neat video. So I'll make sure you could get the links to those and you can take a look at them. All this fancy technical stuff is fine up to a point, but eventually you find a breakdown. Let's see, where were we? Okay, we were at this point. So I'll get those two videos to you. So standing wave ratio is a measure of the impedance matching of loads, in this case the antenna, to the characteristic impedance of a transmission line. And typically for coax, for example, you'll see the coax feed line will be stated with a characteristic impedance of 50 ohms. Typically a transmitter is expecting an impedance match of 50 ohms, so they're designed to have a 50 ohm output to the 50 ohm transmission line. And then the antenna's impedance will vary because it does have reactive components. It's an inductive and capacitive device. You can have varying impedance as a function of frequency. So that is part of the variability that gets into all that. But basically, the idea to have, excuse me, to understand is impedance mismatches result in standing waves coming back and causing the power to be reflected to the transmitter rather than going out the antenna, and that can damage your transmitter. So you need to pay particular attention to the SWR reading of your antenna at the frequency you're operating. And then there are devices, antenna tuners, that can be connected to the transmitter between the transmitter and the feed line to match the impedances so that reflected energy doesn't get back in and hurt your transmitter. Now, a lot of times, you'll put an automatic tuner, antenna tuner here, and a lot of radios and newer radios have internal antenna tuners that will do the tuning for you. And you can get a good match between your transmitter and the input of the antenna tuner. Excuse me, but you'll still have mismatch with the antenna if the impedance isn't matched. You still get reflected energy. It's just that the antenna tuner will dissipate that energy rather than getting back into your transmitter. So just because you have good antenna match here doesn't necessarily mean you're going to get all your power transmitted through the antenna, because you still have a mismatch in this section of the system. Oh, got ahead of myself. So this is the impedance match tuner. This is where it would go. It just shows you what I just talked about. Okay, now we're going to take a look at some SWR plots, standing wave ratio plots. And this is, actually, this is the same antenna. I have this one at home, and this is the same one we have up at the clubhouse, hooked up to the ICOM 7300. But it's an end-fed half-wave antenna. It's not a dipole, it's just an end-fed half-wave. I've got a typo there. And I was measuring it with my antenna analyzer, which is a Rig Expert AA54. And what this is the frequency down here, and then this is the standing wave ratio. And the measured standing wave ratio as a function of frequency is shown here. And you can see for this antenna, we're below 1.5 through the whole range for 40 meters. 40 meters goes up to about 7.3. So we're under 1.5, which is a very good SWR for a real world antenna. Ideally, you'd like to be below 2. And if you have, say, an integral antenna tuner in your transceiver, like if it was a Kenwood or an ICOM that has the antenna tuner, you can generally handle anything 3 and down. So without a tuner, you want to keep it below 2. With a small tuner, you want to keep it below 3. And with you have dedicated tuners that aren't built into the radios that can handle much higher standing wave ratios if that's what you need to do. So this would be a very good standing wave ratio for 40 meters with this antenna, which is one reason we selected it for the antenna up at the clubhouse. It gives us coverage anywhere from 10 meters to 80 meters. And then this is 10-meter band on that same antenna. You can see if over almost the whole band, we're below 2. So you really wouldn't even need a tuner. But with the tuner in the ICOM 7300, when you're actually transmitting, the radio is going to see just about a standing wave ratio of 1 or 1.1. So it's very good for the radio. And looks like I got back into Yagi antennas for some reason. I think this is just showing a little more complicated one. Or one of these is the driven element. The others are reflectors and the director. So the maximum direction of radiation from the driven element is opposite the direction of the reflectors. And then the director is in the direction of the maximum radiation. That's what I couldn't remember which was which, but that's how the direction is determined, with the reflector being a little bit longer than the driven element and the director a little shorter. You can see this is a tower with a rotating drive on it, so you could point the antenna in different directions. This is another type of Yagi. You'll see this a lot in VHF single sideband because 2 meters is much smaller than 40 meters. Obviously, the elements are much smaller, so you can make a pretty structurally sound moldable element Yagi for very good and tight directional concentration of your signals. So you can see how this lobe here, you could spin that around like you could here, and do all kinds of neat stuff with a single sideband. You could build a Yagi like this for 40 meters or 80 meters even, but it'd be huge because those cross members on 80 meters, what they would be 40 meters. I think they'd be 40 meters wide, which is pretty big. Feed line characteristics, different types of coax cable. These are the ones listed here, are fairly representative of what's common. They have different impedances depending on the impedance of your antenna. And the other thing that these coax cables differ is in loss per 100 feet. And this is loss per 100 feet at 28 megahertz, which is a 10-meter band. And you can see that the LMR 400s and 600s have quite a bit less loss than the these grade of coax. So if you have a pretty long run, you want to make sure you use as low loss feed cable as you can afford, and keeping in mind that at the lower HF frequencies, there's not much loss. The LMR 400 wouldn't give you much benefit at, say, 160 to 20 meters in that range. It starts, I did the analysis on that once, and you start seeing the difference at 20 meters between the typical RG8 type coax and then the better lower loss coax. And then you can see that the loss at a higher frequency, 144 megahertz, is 2 meters. VHF, what we talk on our handhelds, the loss really picks up at that frequency for the lower frequency coax. And so for your VHF, UHF, or what I do anyway, for my feed lines, I use LMR 400. For all the HF stuff, I forget which one of these I use, but RG8X, I think, is the one that I use for my HF runs. I think I'm going through this again. Yeah, we just saw this. I must have really liked it because I added it twice to this presentation.
The section's so nice, you went over it twice.
Yep. Another type of antenna you may run into is it's called a trapped dipole. And I'm going to go over an example. I've got this antenna, bought it for Judy, but it hasn't been in service for a while because I since put in my standard dipoles that cover 20 and 40 meters. This is an MFJ antenna that covers 40 and 20 meters in the same antenna. And the way it does it is, if you look at the a drawing of what it is, we've got our feed line here, the coax, and then we split into two elements. And on an element, we've got this length, which is about the length of a 20-meter dipole. And then we put an LC circuit in here, which is a reactive circuit that we can design with different capacitances and inductances to make it very high impedance at the lower frequencies at 20 meters, But then as it gets higher in frequency, the impedance goes down, so it becomes almost a short circuit. And essentially, if you're sitting here, say you're sitting here in this element, and you're looking this way, you see this trap circuit. And what it does when you're at 20 meters, it looks like an open circuit. So what is an open circuit on a dipole? That's a 20-meter dipole right there. So this thing responds as a 20-meter dipole. Then as you increase the frequency, the inductances and capacitances, the reactances of those elements change. So it becomes looking more and more like a short circuit, so that when you get to 40 meters, it's designed so that if you're sitting here at 40 meters, you see this length of antenna, which in combination with the trap circuit looks like a quarter wave dipole at 40 meters. So it's kind of a reactance switch that it switches the 40-meter part of the element on to the antenna when you get up around 40 meters. So if you're up around 40 meters and both of these are turned on, this thing looks like a 40-meter dipole. So you're getting two bands with one antenna, both 20 meters and 40 meters. Now, I mentioned earlier, Mother Nature doesn't give you anything for free. So there is a cost to this, because this overall length of this trap antenna is shorter than a 40-meter dipole. And it's because of the effect of these trap circuits that act as reactance switches to switch in and out that 40-meter section of the antenna. So this was just what I went through trying to figure out how I was going to mount it. I actually put it in as an inverted V. I had the element. I did 10 feet of rope. I put a spring in and then rope to the tree, and then the same thing on the other side. And then I brought the feed line cable in, the coax. I've got a window pass through that I can connect antennas on one side and feed lines on the other side, so I don't have to drill holes in my house to get antenna lines in. A coax, I've got a choke here, and then another 3 feet of coax, and then I hooked it up to the TS590SG, which was my base HF radio at the time. So this is just how I kind of organize what I'm doing when I'm doing a test. So got all that set up and measured the standing wave ratio with my antenna analyzer. And the way this works is this is what is that? That's 5.9 megahertz, and there's 7.150. This is the 40-meter band, and then this is 8.4. So what this showed me when I ran the frequency analyzers on 40 meters is that I had the SWR reached a minimum here, nearly 1, which is ideal for standing wave ratio, but it was at this frequency, which is way below where I needed to be. So what I needed to do and was to somehow get this frequency, this resonant point, moved up into the band where I needed it. Now, a lot of people will say that they have a problem with their SWR and they're trying to get their SWR down. So it sounds like you're making an adjustment to turn something down, like power or gain or something like that. But when you're tuning an antenna, what you're actually doing is you're going to adjust the length of the antenna to move this resonant point, because the resonant frequency is determined by a lot of things, and the biggest thing is the length of the element. So as you make your length of the element shorter, this resonant frequency goes up. So what we need to do is to figure out how much we need to shorten the element to get that resonant frequency here. And this is what I kind of did, the calculations I did to do that. You don't have to use calculations. You can just make a trial and error adjustment to the length and say, since we were pretty far off, I could have moved it, say, a foot, and then run the measurement again and see how much that resonant point moved up the frequency, and then just keep doing that until you get the resonant point where you want it. So if you're tuning an antenna, whether it's a vertical or a dipole, you're adjusting the length to move this resonant point into the section of the band that you want to operate. So this is what I ended up with by working at adjusting the lengths of both the 20 meter and the 40 meter section. I was able to put, this is the 40 meter resonant point here, right in the middle of the 40 meter band, which is where you want to be, so that through the whole band, we're operating under 3 SWR. So the better you're able to adjust the length to get it in the point, the better to this point in the center of the band, the better off your antenna is going to operate. And then the 20 meters adjusted, the length of the wire was adjusted so that I ended up here with this SWR plot like this. Now, one of the trade-offs with a trap antenna is that the lower frequency part of it, in this case the 40 meter band, has a much narrower bandwidth, which is the distance in frequency, say that it's below SWR 3, than the non-trap side, or in this case the 20 meters. We have a much wider range of frequencies on the 20 meter section of that antenna that is below 3 standing wave ratio. So that's one of the trade-offs you get into with doing things like adding traps. You do get benefits, but there are trade-offs to it. And I was working with one fellow, I think he had 3 traps in the antenna. So he had 5 frequencies, I think it was, but it was a devil getting all those adjusted, because when you adjust this one's going to move a little on you. When you move this one's going to move a lot on you. So what I've found the thing to do is to work on the lowest frequency trap side first, get that centered, and then go to the next one and the next one, because the narrower the bandwidth, the harder it's going to be to get it centered in the band, say in 40 meters here. Whereas here you can see this thing could have moved plus or minus a fair amount. I could still have everything under an SWR3. So this wasn't as sensitive to the change of resonant frequency as the other one, because the bandwidth was wider. So that's kind of a real world practical application of kind of a compromised antenna, although there are pluses and minuses for it. Okay, this one. This is going to go through a little case study here on 80, 40, 20 meter half-wave dipoles. These were the ones that I put up in my backyard for Judy to do the PAQSO party. We were using the 80-10 half-wave that we looked at a little earlier, which is a good antenna, but there were some compromises to it where we weren't getting quite the reception or quite the propagation that we could get with individual dipoles. So this is a little, this is just for my records. This is how I did the calculations to move the frequencies. But I used a similar approach to what I did on that 40-20 trap antenna, where I take the standing wave ratio measurement across the band. Here's 4.0 megahertz, and here's 3.6. This is the single sideband portion of the extra station for phone. Now, what I wanted to do was put the resonant point in the middle of the general section, which is where Judy was going to operate. So based on the first antenna measurement I took, I was going to have to move this point to here. So that's what I calculated, how much I had to shorten that dipole to get it to where I wanted it to be. Again, you don't have to calculate it. You could do some trial and error and tune it in just fine there too. This was the 40-meter dipole. Same thing. Got our SWR plot, and I wanted this to be in the middle of the general single sideband, which would be in this range here. And I got it fairly close, but even at that, even though I wasn't exactly where I wanted to be, I was less than 1.5 through the whole range I wanted to be. So that was a good fit for what we needed there. And then did a similar thing with 20 meters. Actually, what I've got here, I didn't figure out till after I ran this chart. This is what you get when one leg of the element is a little shorter than the other leg of the element. I had misadjusted the elements, making one shorter than the other, and where you would expect this to come down and be a smooth transition, I actually got this little deviation here because of the dissimilar lengths in the dipole. So that was a good experience to find that out. So it's another check when I'm making measurements now. And finally, this is another case study of a dipole. This is Alpha Antennas Hextenna. And what it is, it's a dipole that can be set up anywhere from 2 meters, actually 440 megahertz, all the VHF, UHF frequencies, the 3 bands, and all the HF frequencies. And Judy spotted this at Ham Nation last year when we were down there. And they had this dipole in display. They didn't have the tripod, it was just hanging up in the air. And there were these 2 long elements. And it caught her eye, I think because it looked neat. But as soon as I looked at that, I saw that since these are telescoping elements, that antenna would be infinitely adjustable in length. So I could adjust the resonant point on any band exactly to where I wanted it just by adjusting the lengths of the 2 dipoles. So we ended up buying this thing. And this is how it's mounted on a tripod. It's got a little, I think there's a baling in here. I'm not too sure, I haven't opened it up. But you have these 2 telescopic elements that you can adjust to any length. So the manufacturer gave you some lengths for the different bands that you could use. So it was a starting point. And what I did is I set that antenna up in our backyard, set it to his readings, and then this trace, for example, this is on 40 meters, is where it was the way he set it up. What I wanted to do was to put the resonant point right in the middle of 40 meters so I get the lowest standing wave ratio over the whole band. So I was able to calculate how much I had to shorten it to do that. So this is, I started here, I shortened it and ended up here. So you can see, because I had the ability to infinitely adjust the length, I was able to put it dead nuts where I wanted it to be. And then this is 20 meters. You can see the resonant frequency 14.288, put right in the middle of the general single sideband band, so we get the best standing wave ratio across the whole band that Judy operates. And the other thing is that noted is that the magnitude of the impedance of the antenna was 50.6 ohms, which is nearly an ideal match. So that was good to see. And then these are the other bands that it can operate. So I was able to tune it very well. So any band we go to, we can have the low standing wave ratio right in the middle of the band and give us the best opportunity to operate. They didn't advertise it for 6 meters. They just advertised 10 to 40, but we were able to set it for 6 meters and operate there as well. So what I ended up doing, these were the factory, maybe not. I took the factory settings out. These were the values I ended up with, the length of the elements to get these SWR plots. So now all we have to do is when we go out, say if we're setting up for 20 meters, I set it up, put the elements in, extend them all the way out, and then I shorten each side 8 inches. And then that puts me right dead nuts here. So it's a real handy way to go to multiple bands with a minimal adjustment needed, because we did the homework beforehand and we know what has to be adjusted. So each one of these had different objectives to it, different problem statements. But you can go through all the math and physics you want on antennas. What it really comes down to is the performance. And this is a plot of using that hex antenna we just looked at, doing parks on the air when we were down south. We operated in one park in Florida outside of Orlando, and then we went to New Orleans. I think we did 3 or 4 parks there, and these are all the contacts that were made with that antenna, which is extremely good range for a portable antenna. And we hit Puerto Rico, and I forget what this is, some island off the coast of Africa. So that was pretty good. And then this was from here. I don't know how many activations we did, but you can see this is pretty much 40-meter area here. And then the 20 meters tends to be farther out in distance and have an occasional European, African contact. So that's how that antenna performs, which is extremely good. Judy gets good signal reports on it. So all that stuff seemed to work.
Sometimes.
Well, she thinks the antenna gets bad, but what happens, the bad conditions change on it. So
now in the last slide,
yeah,
I'm assuming that your antenna is pretty much pointed north-south, correct?
yeah, right.
So then it propagates east-west. Okay.
Right. But you can see, even with its north-south, we still get pretty good coverage down here.
Right.
And you don't get
But if we wanted to talk to
contacts up
Columbia, take the antenna, turn it 90 degrees, and we've been talking to Columbia.
Right. And you can
Gotcha.
see we don't get many contacts up here, but it's not the antenna. There's not that many hams up there. It's pretty desolate territory.
There you go.
So you know, there's no hard and fast analysis you can do. I don't think. You just kind of get a general read on how things are performing. But I know one thing, like the 8010 infed half wave that we have up at the clubhouse, and I have one here. I've worked Australia on FT8, which is a digital mode, just about any time I want to in the morning. And, you know, that's 10,000 miles away, but it's a low, weak signal mode, and so it's you know, there is no perfect antenna, and but like I said, the real key is to be an effective with your antenna selection is to have a good definition of what you want it to do, because if you don't do that, you'll want to try to do everything, and Mother Nature's just not going to let you do it. So that's about all I know, I think. You got any questions?
No, actually, that was probably the most easy to understand lesson I've had so far.
Well, good, because it's probably the most difficult subject. So
Really?
that's a good thing. Well, it's
There
the
you go.
one that people kind of get tangled up in, and they don't pay attention to the details. They don't think it through, or their expectations are out of line. Um, I'm working on a project right now. What we want to do on Parks on the Air is they have awards for the number of parks you activate in a day. Well, what you have to do is set up a system so that you pull into a park with minimal setup, get on the air, make 5 contacts, and then leave. Well, that hex antenna takes a while to put up. You know, it probably takes 10 minutes to set it up, 10 minutes to tear it down. But it's a good antenna to work a lot of contacts. If you're wanting to work contacts for a couple of hours, you could get 100 QSOs in that time frame. But the objective of this antenna system is to be quick, get your 5 contacts, tear it down, and get out. So I've got it set up to where all I have to do is screw this antenna into a mag mount, and she's on the air. She can get her 5 contacts, and I'll unscrew it, put it in the car, and we move on to the next part. Now, I did the analysis today on it, and I got very good SWR over the range we want to operate. But there's a parameter called return loss, which gives you an idea of your effectiveness in radiation. And we're not going to get the radiation capability in this small vertical that we had in the hex antenna, but that's not unexpected, you know, because the compromise is it's a smaller, shorter antenna. So I don't need to get out to California with this antenna. I just need to get 5 contacts. They could all actually be in the state of Pennsylvania rather than all over the country, and I can satisfy the requirement for the problem statement. So that's why it's so critical to understand what you're trying to do, and then keep that in mind when you're operating, because you made decisions of compromise in order to get to your best solution. And if you start thinking about, well, gee, this ought to be able to do this or that, and it wasn't intended to do that, then you get a little frustrated.
Nope, makes sense.
So that's about all I know. Hopefully I'll know a little more tomorrow. So how you coming on your test? I'm going to stop the recording. Well, let's see.
I haven't been taking them every day like I want to, so it's still in that, you know, between 50 and 60 range.
Oh, okay. Well, let's see. We've still got about 3 or 4 weeks. Yeah, I'll be able to close out with no trouble. I think
Yeah, we're hoping.
just stay at it every day. You know, if you can find 15 minutes a day to go through 3 tests, it's probably about all you need to do.
Yeah, that's what I'm trying to do. Is, you know, I check the flashcards, I run through a couple tests. You know, that's.
Well, just think, if you get the extra, then you won't have any more tests to take.
Believe me, I'm usually taking the general, and then I try to do an extra. Last one of those I took, those like closer to 40%. So.
Yeah. Well, you can do about everything you need to do with the general license, so that's the key.